Bismillahirrahmanirrahim. I'm going to treat a very simple problem which is basic to running regression models. Anybody who uses regression should know these things. However, very unfortunately, 90% of the people who are running regressions don't know these things. So we get these papers submitted to PDR and to other journals that I run, which are just wrong because they don't understand ABC of regression methodology. So this particular paper is only about ABC. There's lots of more advanced techniques, and in fact I gave lecture on this earlier to the faculty. So after the lecture I got some feedback and tried to see if the message had gone through, and it turned out that because I was covering a lot of topics at the same time, that it seemed to me that most people did not understand. So this particular lecture is sort of a revised version in which I will concentrate on making only one point. And that one point is the first thing that one needs to know about regression. And what I would like to do is to make sure that this minimal standard is met by all papers which are submitted to PDR at the least. So I will refer to all authors who submit papers to listen to this lecture and revise their paper in light of this. Alright, so the basic issue that we want to ask is, if I have a regression model, if I'm running, for example, I want to know if FDI affects growth, for example. So is it enough for me to take a regression in which growth is the dependent variable and FDI is on the right hand side and run the regression and get the results? The answer is no. Unfortunately, most people don't realize this. So why is it no? So that's what we would like to see. So I would like to start by saying that there are three papers. All three of these have been submitted to PDR. One of them deals with is about intellectual property rights and its effects on growth. So it is a regression in which GDP is run on some supplementary regressors which are not important, but the author put them in because he said, okay, IPR is not the only thing which matters. And so then he added IPR, he ran the regression, he looked at the estimate of IPR, the coefficient, and he interprets that yes, if this is positive, then IPR affects growth positively. If it is negative, it affects negatively, and if it's strong and powerful, so the standard which everybody knows how to interpret. So then there is a second paper which is just about export-led growth, and it does the same kind of thing. It uses a different set of supplementary regressors, and then it adds exports, and it does the same thing, that okay, if the coefficient is significant, then we should have, that means exports matter for growth. If the coefficient is not, then exports don't matter. Exports is negative, then exports will affect adversely. So this is the standard. And there is a third paper submitted to PDR which deals with the FDI and human capital. So it has two variables. One is FDI, and there is literacy. Literacy is a proxy for human capital, and then it goes through the same analysis. So now the first question that I would like to ask is, can all three of these authors be right in their interpretations? I actually asked this at one interview for which we were conducting for lecturers and professors at Econometrics, and the person was teacher of Econometrics courses, and he said yes, this is the standard. If I want to find a fourth thing, I want to find the effect of climate on GDP, then I can do exactly the same thing. I take some central regressors, and then I add a climate variable, and I ask, does climate matter? And I look at the results. So the basic question is, so all of these papers are right. The IPR paper gets the right result for IPR, the export paper gets the right result for exports, and the human capital paper gets the right results for exports. This is the standard understanding. And in this, I cannot blame the students who come up with this, because although the econometrics textbook teach you that this is not correct, this message is very much suppressed and hidden. And the reality is that what the students learn how to do, because nobody ever warns them that this is wrong, is that they learn to believe that this is the right methodology, which it is not. In fact, these three models are in conflict with each other, and it is impossible for all three of them to be right. At most, one of them can be right, and most likely all three of them are wrong and coming to the wrong conclusion. So Edward Leamer first pointed this out in his book, which is called Specification Searches. He says that, well, there's a very great disparity between what he used a colorful metaphor. He said that, we were taught the classes in the 5th floor of the Chicago school, and there people were saints, and they would tell us that this is the pure methodology where you know in advance the right regressors and you put them in, and you never experiment. You're not supposed to experiment, because as soon as you experiment, you throw out one variable and put in another one, then all of your basic statistical tools for judging significance, etc., they all become invalid. So he said that when in the upstairs, this is what they preached, but when you went to the basement, then they all became devils, and they did everything which they said you cannot do in the 5th floor, and in the computer lab was in the basement. So he said that basically the econometrics textbook teach you that the regression is valid only if you have these assumptions. Everybody memorizes these assumptions of the regression model, 5 or 6, and then it is never mentioned again. I mean, after you meet these assumptions of the regression model in the chapter 1 about exogeneity and this and that and the other, linearity, normality, etc., etc., you never meet them again. But the fact is that these assumptions are of crucial importance. If the regression results are valid only if all of your assumptions are correct. If any one of your 5 assumptions or 7 assumptions or 12 assumptions fails, then your regression results are not valid. This is just simple. 2 plus 2 equals 4. Nothing strange or new or difficult about this. So I'm not going to deal with all 5 of these assumptions or 7 of these assumptions. I'm going to deal with just one assumption. One of the assumptions of the regression model is that you have all the right regressors, that all the regressors that you have included are determinants of the dependent variable, and everything that you have excluded is not a determinant. So you have exactly the right set of regressors to begin with. You're not allowed to test. You should know that this is the right model. If you have included the wrong regressor by mistake, then the results are not valid. If you have excluded a correct variable by mistake, again your result is not valid. So both the inclusions and the exclusion must be correct for the model to be valid. So now, if exports model is correct, then that means that the exports is a valid regressor, and the other two must be wrong because they have excluded an important variable. The same thing is true for all 3 of the models. And all 3 of the models can be wrong if there is some significant variable which is not included in any of the 3 models. And that is the most likely probability. So this growth regression, this is one of the most heavily explored issues in all of the econometric literature. So in fact, people have run this regression on the WDI dataset, which has about 60 variables available for a large set of countries which are said or thought to be related with growth. So if any one of these 60 variables is a significant determinant of growth, and if it is excluded, then the result that you have is not valid. So many people have done this. So now the issue is that leads to about 2 to the 60 models, which is a huge number, millions and millions and maybe trillions and billions. So how can we find out which one of these trillion models is the correct one? Because the axiom of correct specification says that unless you have the correct model, which is if you just pick regressors at random and you play with them at random, your chances of picking the right model are 1 in a trillion. So if you just say, okay, I like these 5, 6 variables and I'm going to run a regression, then you're already dead, because that's not going to be the right variable, right model by any means. There's just no chance. So how can we get to the true model? The standard methodology is to use R squared or AIC or BIC or Schwartz criteria or many other criteria that have been devised. These are the model selection criteria. So basically the goal is to run through a large number of models and pick the best one according to your model selection criteria. But this doesn't work, because how many models can you examine? 100, 1,000, 1 million, and run AIC on all of them. And actually you can show that even if you manage to run 1 million regressions and select the correct one, the problem is there's lots of noise. These things are not, these AIC, BIC, etc. These are all statistical measures. They have some fluctuation. So near the bottom, you're trying to find the one with the minimum, there will be lots and lots, thousands and thousands of models which are close to the minimum AIC. So if the minimum AIC is 1.29 and you have something which is 1.28, you can't say that this is wrong, because that much difference can be made just by random error. So now once you admit that it's not the AIC is not the perfect tool which always tells you exactly the right thing, if there is any amount of noise, then you will end up with thousands of models which are very close to having minimum AIC. So again, this is not a reliable method to get to the right model. So the key problem that we face is how to ensure that there are no missing significant variables in the regression. Because missing significant variables can cause disaster. Now the other problem is how to ensure that there are no extra variables that are included. Now that is not as bad. If you include variables which are not relevant, that does cause you some harm. It lowers the efficiency of estimation, but it does not lead to inconsistency. So that's because if you have an extra model, if you have an extra variable, the value of 0 is possible value of the coefficient. So the model nests the true model. The true model is within the class of models that you are considering. So in that case, the inclusion does not cause as heavy damage as exclusion does. So the major lesson from this is that we should start with big models, because as long as our model includes the true model as a special case, there are the problems that arise are of a lesser degree than the other case where you exclude a significant variable. So this is the first thing that we want to look at. How much trouble can a missing significant variable cause? So we start with a simple standard regression of Pakistan consumption and Pakistan GDP, and it comes out nicely and naturally, as we all know. So consumption is equal to 4 plus 0.88 times GDP. R squared is 0.998. Now, it is very likely true that there are some missing variables here. This is a simple Keynesian consumption function. There might be lags, there might be other effects. However, there is something going for us here. That's the whole integration co-integration theory. it turns out that if consumption and GDP are co-integrated, which is likely to be the case, then you have something which is a phenomena which is called superconsistency. And superconsistency means that the coefficients converge to the right values at a very fast rate. And that means that even if you exclude, even if you have misspecification here, if you have excluded the lag of consumption and if you have excluded FDI or interest rate or whatever, which are important determinants, still you will get a reasonable result. The lesson to be learned from this is just that if you have the major primary determinant of your dependent variable, and if the major primary determinant is a trending series, so it's a it becomes very big very quickly, then the effect of this can be estimated even if you don't know the exact specification. So this is one good news, a positive result. Most of the talk will be about negative, but this is one positive result. But now, to go ahead with our agenda, suppose that I don't know, and this is the typical case that we are exploring, that I want to know, does intellectual property rights matter or not? So I don't know what the determinant is. So what will happen if I experiment? So I did. I took two variables from the WDI, picked completely at random. One of them is survival, SUR. This is survival to age 65 of the females as a percentage of the cohort in Pakistan. And then there is CO2, which is the CO2 emissions from gaseous fuel consumption as a percentage of the total. Obviously, these variables are not really related to consumption, but here's the regression. Consumption equals, R squared is 0.84, not bad. SUR is highly significant, 6.78, and the standard error is 0.73, so T variable is astronomical, and this is 99.9% significant. And similarly, CO2 enters with a negative sign. So obviously we understand that if the female survival rate becomes higher, then consumption will increase because females eat a lot. And obviously, if the carbon dioxide emissions go up, then we will stop. That will harm our health, and so we will reduce our consumption. This is the kind of thing which every student in this kind of nonsense that every student who runs a regression learns to say. That okay, here's our regression, the variable is significant, and now we interpret them, and we have a thesis. Now there's new MPhil thesis waiting for anybody, how the female survival and the carbon dioxide emissions affect new theory of consumption. So this is called a nonsense regression. Why is it nonsense regression? Because of something which is not taught in econometrics. It's because there is a missing significant variable. So the GDP which we have omitted is a missing significant variable. This regression is misspecified and it cannot be interpreted. So the same thing is true of any regression. When you put down a regression and you start interpreting results, then you are saying that I guarantee that nothing important has been left out of this model. If you are prepared to give that guarantee, then we can listen to your interpretation. If you are not guaranteeing, you never even looked at what other possibilities there were, then the regression is just completely meaningless. That's nonsense is the correct word. It is a nonsense regression. All your interpretations are nonsensical. And the reason for this can be understood by mathematics, but it's basically that when the variable is missing, then any included variable acts as a proxy for the missing variable. So however much this variable is correlated with the missing variable, that is the way that it will come into the variable, and it will become significant because the significant thing has been missed, so it acts in its place. So we can show that this is the case by adding in the GDP, the missing variable. Once we add this in, then CO2 and survival, they both become insignificant. And so the nonsense regressions are caused by missing important determinants. Now this is something which is actually, I would say that a discovery of our Professor Atiqur Rahman here. And this is not at all understood. I mean, there's a whole theory. For 30 years, people have been talking about spurious regressions and nonsense regressions, and they have not understood. And this whole theory of integration and co-integration, this can all be thrown into the garbage. Because this theory was invented to explain why do we see nonsense regressions. And they say we see nonsense regressions because if you run consumption on Y, these are integrated variables, and when you run integrated variables, you get nonsense regressions. And the only way to avoid that is to check for co-integration. If you have co-integration, then even with integrated variables, you get correct regressions, not nonsense regressions. This is the standard theory which is currently taught in all econometrics, and it's completely wrong. It's a nonsense theory. And actually, Atiqur Rahman has now working with somebody to develop the alternative. And basically the issue is that nonsense regression is caused by a missing significant regressor. So if you take, and we do this routinely in econometrics to show this, that if I take consumption of Nigeria and I run it on the GNP of Bolivia, I will get a significant regression. Because the standard explanation is why, because both of these variables are integrated. And so when you run integrated variables, now this doesn't make sense, because actually if you look at the theory of integrated variables, and you find that it is true that this happens when you run in an integrated series on an integrated series, you get significance most of the time, but not all of the time. And these cases that we are talking, we get this all of the time. So that's one thing. The other thing is that the integration property itself is something which cannot be easily established, and there's huge amounts. So we cannot be sure that, I mean, if you are saying the explanation for the nonsense regression is that both of these series are integrated, there's no proof of that. We don't know whether the consumption series of Nigeria is integrated or not. We cannot establish this, because the integration property is something which can be established only for very large time series. Somebody who has done tests said that when you have a series of length 100, then you begin to get some correct results. Otherwise, the integration tests and co-integration tests have very low power. They cannot detect whether a series is integrated or not. So the idea of explaining nonsense regression by integration and co-integration is wrong. But the idea of explaining it by missing variables, this is correct. If I run consumption of Nigeria on consumption of Bolivia, I will get a high R squared and significant GNP of Bolivia. But now if I put in the GNP of Nigeria, then that variable will become insignificant, showing that this is a nonsense regression, because the key determinant was missing from the variable. So once we take this into account, then the whole theory of nonsense and spurious regression, which has been developed over the past 30 years, just becomes useless. Alright, so the basic lesson is that omitting significant regressors lead to nonsense regressions. So if we come back to the original question, are the models 1, 2 and 3 in the papers that were submitted to PDR, are they correct? So the answer is we don't know, because we cannot know whether or not significant variables were omitted. So if somebody finds that the IPR is significant, we say, well, are you sure you have included all relevant variables? Maybe exports should be included. If I put in exports, then maybe IPR will become insignificant. How do I know? The other guy says that human capital is important, so maybe I should put that in. And if I put in human capital, maybe the other two will be excluded. So who knows? And this is not something, this is hypothetical. This happens all the time. If there are two variables, if I exclude one, the other one will become significant, and if I include it, it will become insignificant. This is something which is very routine. So this is something which Edward Leamer has studied in his book Specification Searches, and that's where he came up with this idea of the axiom of correct specification. He said that, well, suppose I don't know the specification. Then I can say, okay, I'll try things. So we have millions of things to try. If you have 10 variables, then I have 2 to the 10, 1024 possible models. And by trying different models, I can get any result I like. So in particular, this is, you have heard of this book, How to Lie with the Statistics. So if you want to learn how to lie with econometrics, if you have one variable that you want to prove is important, like IPR for example, then basically the trick is to choose the right set of other variables. If you change those other variables, you can get whatever result you like. By choosing those other variables in a certain way, you can make it positive. By choosing in another way, you can make it negative and significant. By choosing them a third way, you can make them zero and insignificant. And if you know something about the multidimensional geometry and the correlational structures, you can easily do it. And you have theoretical ways to choose these variables. But even if you don't, you can experiment at random and get the result that you like. So you can prove whatever you want. IPR is positive, IPR is negative, IPR is not significant, whatever you like, by choosing the right set of auxiliary variables. So the process of regression, so this gave Edward Leamer a very unique insight, which unfortunately has not been understood by most people. The title of the book is the Specification Search. That basically, you see, we present a regression model as an attempt to find out something about reality by choosing regressors. But the truth is entirely different. It is actually that we already know that GNP is a significant determinant. We are trying to prove this by selecting the right model. So we already have a hypothesis that IPR will affect GNP in such and such way. For example, it comes out most clearly in export-led growth. I'm not looking for the regression of growth on exports. I'm trying to find the specification which proves that exports have a positive effect. And I'm going to search through the models until I get a positive and significant coefficient. And so this is what a specification search is. I already know the result that I want to get, and now I'm going to change the variables until I find this result. And I can do it. This is exactly the point of the specification search. So here is Leamer's proposed solution to this problem. He called it the extreme bounds analysis. He says, okay, suppose that, so he says, there is a focus variable, that's my W, that's like intellectual property rights. I want to know, does IPR matter or not? So now there is this specification search method that I can make it matter by choosing the right collection of variables. But suppose I want to be serious and I want to really know, and I want to do what we are supposed to be doing, that is to discover whether or not W matters. Then I have to proceed in a different way. First, we choose some fixed relevant variables which are guaranteed to be important from theoretical consideration. So basically, I include everything which theory says must be included, because if I exclude one of those, then I am automatically misspecified and nothing can be said about the regression. So those are the initial variables, x1, x2 through xn. These are the variables that must be included. Then I put in my candidate variable w. Then I put in the other potential determinants, things which might or might not matter, v1, v2, v3 up to vn. So now there are three types of variables. There are significant variables which are known to be important, that must be included in the regression regardless of anything else. Then there is the variable which we want to assess, and then there are other possible candidates like So W could be IPR, then the other variables could be trade and human capital and this, that and the other, everything else. In fact, all the other 60 variables in the WDI dataset must be put in as potential alternatives, because if I miss any one significant variable, then my result will be wrong. So what Leamer says is that, okay, try all of these regressions, and in all of these regressions, if your W comes out significant, then you can say it's significant. That's called extreme bounds analysis. Right? So this is a sensible idea. Okay, I tried everything, and regardless of what variable I put in, W always comes out significant. So now you cannot say that I'm missing some significant variable, because I tried all of the variables, and even with all possible variables, it always comes out significant. Now, the people tried to do this, and unfortunately, the Leamer method fails in the following sense, that you cannot find anything to be significant, because basically, when you try this method, then after you put in all the variables, every variable becomes insignificant in combination with some other variable. So basically, the extreme bounds analysis did not proceed anywhere. So Leamer said that inference is very fragile, it's very dependent on the whims of the investigator, and basically there is a pessimistic and negative conclusion that the data does not allow us to tell whether or not the variable W is significant. That is the conclusion that Leamer reached. But there were other people who had more hopes. So there was Sala-i-Martin famous article called "I ran 2 million regressions." So he said that, okay, I will take Leamer's EBA, but I will modify it a little bit. So because Leamer's original method, leads to despair. You can never find anything. Nothing is significant. So he sets. So I'm going to describe this in detail, because this is something which is currently going on. So he said that, okay, let's start with these 62 variables. These are our 62 variables on which I have data. I'm going to put in all of them as determinants of growth. So I want to follow Leamer's method. So I choose 3 as essential determinants, and he chooses GDP in 60. I think it's 60 means it's real. I mean, it's 1960 is the base year. Life expectancy and primary school enrollment. So one is human capital and the other is health. This is the standard human development idea, that these are the things which matter for growth. So he said these 3 variables I'm going to include in all of the regressions. So this is these are my primary variables. He says that these 3 are important regardless, and so I'm not going to look at them. I'm not going to vary them. But so that leaves me with 59 variables. So now I want to know which of these 59 variables is important. So I'm going to do it by Leamer's method, but a simplified Leamer's method. So I choose any one of them as focus variable. So I choose X1, for example, which may be the proportion of Protestants in the population. Remember that this is a panel data set, WDI data set for 160 countries over 60 years. So Protestants turns out to be, the percentage of Protestants turns out to be a significant variable. So you put that in, that's my W. Now I want to put in all other combinations as additional variables to test whether this remains significant. But he makes 2 deviations from Leamer. One is that if you include all possible variables at that time, it was still beyond the capabilities of the computers. It would run for days. So instead of, he said that I'm not going to put in all variables, I'm just going to put in 3 variables from the remaining, remaining 58 variables. So 3 are primary variables. I have focus variable, which is percentage of Protestants, and that's 4. So I'm left with 58 variables. So I'm not going to put in all combinations of 58. I'm going to put in all all combinations of 3 variables chosen from these 58. Okay, so that's still millions of regressions. So now I put in all 3, and then so that's one variation. Instead of putting in all possible variables, I'm just going to put in groups of 3. So hopefully, if there is significant variable missing in 1 or 2 or 3, then I will capture them, and then the problem that I initially discussed will be avoided. The other difference that he makes is he says that I don't ask for this variable to be significant in 100% of the regressions I run. I only want it to be significant in 95%. So slightly relaxing the criteria of Leamer. So if W is significant in 95% of these regressions, then I will count it as significant. So I counted that there should be about 10 million regressions. I don't know why he said 2 million. So when he followed this procedure, he came to the conclusion that 22 variables in this set of 58 are significant. That is, when you put them in, they are significant by themselves, and with any combination of 3 remaining variables, they remain significant in 95% of the cases. So that was his result, that we don't need to be pessimistic. If we apply original Leamer extreme bounds analysis, we cannot tell about any variable whether or not significant, but with his Sala-i-Martin methodology, I can find 22 variables which matter and the others don't. So now actually Sala-i-Martin's analysis is wrong. Why is it wrong? The analysis is self-contradictory. If the 22 variables are all significant, then all regressions which use less than 22 variables have a significant omitted variable. So all of the regressions that Sala-i-Martin is running, all of them have maximum 7 variables. 3 of his fundamental variables, 1 focus variable, and 3 test variables. So all of his regressions are misspecified, and by the analysis that we already did, we can't learn anything from any of them. So the whole result is just nonsense. Can you get sensible results by running 2 million nonsense regressions? No. The answer is no. So basically, the results of Sala-i-Martin are wrong. And there was a simulation done by Hoover and Perez later. And he said that suppose that we take, he constructed an artificial data set in which he chose some good regressors which determine the dependent regressor, and then he chose some unrelated regressor. In simulations, we can know. On real data sets, we don't know what is the determinant, but in an artificial simulation, we can control which is the determinant and which is not. And he did that, the Hoover and Perez study, and they found that the Sala-i-Martin, and then they said, okay, what if we follow the Sala-i-Martin strategy to find the significant regressors? So he found that it has both very high type 1 and type 2 error probabilities. It can include many irrelevant regressors, it can exclude significant regressors, and tends to include too many regressors as being relevant when they are not. So the simulation tells us that if you follow Sala-i-Martin strategy, which is a variation of the extreme bounds analysis, it doesn't work. It doesn't find out the true variables when you know what the true variables are. So there is another strategy which was done to modify the extreme bounds analysis, which is a pure Bayesian strategies, and he takes 41 regressors from the Sala-i-Martin datasets. This is Fernandez, Lay, and Steele, and he uses a purely Bayesian approach in which he assigns a prior probability to each of the variables, that this has a certain prior probability of belonging to the model. Then using an extremely complex Bayesian procedure, which is really because it requires putting a prior on trillions of models. This can be done, but basically only by the latest computational techniques. This is because now we have the supercomputer power to be able to analyze trillions of models in a Bayesian way using recently developed techniques like the Gibbs sampler, etc. So he comes up with posterior probabilities, and he finds out that there are 3 variables which are strong determinants, actually 4. One is the percentage of confusions in the population. The other is GDP 60, equipment, investment, and life expectancy. These are the strongest. These are the ones which receive the highest posterior probability. Now, if this analysis is correct, for example, then all of our 3 submissions are wrong because they don't include life expectancy, they don't include equipment investment, they don't include confusion percentage. So if they are missing significant regressors, then all of these 3 submissions that we received to PDR, we can throw them in the garbage because they have omitted a major determinant, and therefore they cannot be right. So there is a controversy about there are actually 2 different goals in model selection. One is to produce a good forecast, and one is to find the true regressors. So it turns out, and this is something about which there is a huge amount of confusion and debate, that there are 2 different goals and they have different strategies. So if I want to produce a good forecast, then the Bayesian method is a good method, and what the Bayesian method ends up doing is that it does what is called model averaging. So it takes a lot of different, thousands and thousands of different models, and says, okay, this model has probability 1%, so I will take its forecast and put it with the 1% weight in my forecast. And so I take 1,000 different models. And so some people attack this approach, saying, and there's a regular debate in the literature, that look, what are you doing here? You have only one true model, so you're taking 999 false models and one true model, and you're averaging all of them. How can you possibly get a good result by this? So it turns out that basically forecasting by so the other method is to try to find the true model and then use the true model to forecast. But now it turns out that the chances of our selecting the true model are very low in these situations because there are trillions and trillions of possibilities. So if I do this, then it's like putting all your eggs in one basket, and it's a very high risk strategy. So if you're doing forecasting, then it is better to do model averaging, and that is best done by Bayesian procedures. If you are doing model selection, and model selection means I want to know, does IPR matter or does it not matter? Then model averaging is useless because it will not give you the answer. Then you have to do model selection. You have to, and so different techniques are appropriate for these 2 different goals. So what we are concerned with in this paper is model selection and not forecasting. But there is some confusion which exists, so I wanted to clarify that for forecasting, selection is not important, contrary to what one might think, that it might be that we might think that if I can select the right model, that will help me to make the right forecast. But it turns out that in real data, it doesn't work like that. If you want to forecast, you don't need to select the true model. But for very many important other purposes, like learning about the structure of the real world, we need to know what the true regressor is, and in that case, model averaging is not good. And another thing which is not good is the forecast criteria. There is this well-known idea, repeated in even in your model selection criteria, that the model is true which forecasts well. So it does not true. It may be that your the best forecasting models, which will be collection, are not the true models. This is not relevant to my current talk, so I won't mention this more than that. But it seems paradoxical, but this is true, that the false model can forecast better than the true model. So the Bayesian model averaging fails to find the right regressors, but it does well at forecasting. So now we forget about this issue of forecasting well, and we turn to the idea of how to find the true model. And for that purpose, the Hendry methodology of encompassing is the right tool. It is not the right tool for forecasting, contrary to what the literature says, but it is the right tool for trying to find the right model. So Hendry methodology starts out by noting that if you use conventional econometrics methodology, which is what the paper submitters to PIDE are doing, then you end up with conflicting and contradictory theories and models. Everybody comes up with his own set of 5 regressors, and here's my regression and here are my results. Now, there cannot be multiple papers on the same topic. There can be only one paper on one variable. So, everybody runs a new regression, and we can find papers in the literature which prove that exports cause growths, and multiple papers, and then growth-led exports, that growths cause exports, and then two-way causality, and then no causality. So all 4 of the hypotheses, there are multiple publications. Why? Because the methodology that we are using is fundamentally incapable of identifying the right model, because it never tests to see if there is a missing significant variable. And because of this, there is no accumulation of knowledge. 10 people put 10 different models, and the 11th person comes and put in the 11th model. So what Hendry said is that no, this methodology is wrong. Suppose I have 10 different models, then I need to find a model which nests all of them. One model, one big model in which all other models are included as special cases. So at the end, I should have only one model, and my one model should have the property that it is better than all existing models in the literature. So this is called encompassing in a general literary sense, that when I write a paper, then the model that I propose should be better than all existing models. So at one point there is only one champion model. This champion model should have the property that it beats all other models in the field. In that case, this qualifies as a worthwhile model. Now, the standard strategy followed in econometrics is that everyone can make a new model without any concern for whether his model or her model is better than other models or not. And as we have said, this is wrong. This cannot be, because if somebody else has a right model, then your model must be wrong. You can't have 2 different models, both of them being right. So how do we do this for choice of regressors? Again, the general methodology is big. I'm going to take only one small, simple, special case. And so the basic Hendry idea is to talk about the GUM, the general unrestricted model. So he says, make the biggest possible model. Add all relevant variables. So in terms of a practical strategy for running regressions and writing papers, you collect the literature, you will take every possible paper which has been written on your variable, and you gather all of the variables which anybody has ever used, and you put them all into your general unrestricted model. Now you have a model which is capable of, for which you cannot say that something which somebody considered significant has been omitted. This is still a big restriction. There may be something which is missing, but now we are talking about what is feasible to do rather than what is ideal. So now, so for the particular example, what I could do is I could say that start with a GDP, and I put in IPR, and I put in FDI, and I put in exports, and I put in all other significant important variables and now I look at what comes out significant in this regression. So at least in this regression, nobody can say that you have omitted a major significant variable. So in this regression, if I find IPR is significant, then I have some chance of saying that IPR might actually matter, unlike the original case. And if IPR comes out insignificant, then I can say that, well, no, it's not significant. So the conventional methodology in econometrics is called the simple to general methodology, and it starts with the simple model, and if somehow this model fails to give you the right result, then you add more variables to make it work better. Now, as I said, this strategy is obviously wrong, because if you start with a simple model, it means almost surely that you're missing some significant variable, and if you're missing some significant variable, then anything can happen. So your simple model is almost guaranteed to be wrong. So the flaws of this strategy is that okay, I already discussed. So the alternative is called GETS, General to Simple Model, by Hendry. So build the largest possible variable regression. So in the Sala-i-Martin data, you run a regression all the 61 variables, and then you drop the insignificant variables, and that is how you get to your simple model. But there are some tricks and complications that I would like to explain. So there are many people who had, the reason this is not common is because there are many strong objections that you can make. And basically the first objection is that you have small amount of data and you will have a lot of multicollinearity, so you will not be able to interpret your results. So if you, it's well known that if you put in a lot of different regressors which are irrelevant, even in your consumption equals alpha plus beta g and p, if you start putting in too many irrelevant variables, your important GDP variable will become insignificant at some stage, simply because you don't have enough data to estimate things that precisely. So you have multicollinearity, important regressors will fail to be significant, noise, you see a lot of noise is introduced, and noise can exceed the signal. So bad regressors can drive out the good ones. So this is a problem with the GETS methodology, but these problems have now been resolved, and a lot of progress has been made in getting a sound methodology for general to simple modeling. And so how do you, it has basically, currently it has an 80% chance of picking up the relevant regressors, plus one or two extras. So in general, so with there is now an automatic built-in package in PCGIV, in which you just feed all the regressors and it runs through this methodology and gives you the final model. And basically, actually, Hendry wrote a paper called "We Just Ran One Regression," in which he took the Sala-i-Martin data set and he fed all the 61 variables, and then he got out the final model, which was not too different from the one that was obtained by Sala-i-Martin. No, actually, but there were some significant differences actually. So GETS is not actually a mechanical procedure. It must be guided by knowledge, in the sense that we can show many examples where if I put in two variables, the wrong variable is significant and the right variable is not significant. There are many published examples in the literature that, example, in the famous Hendry error correction model, there are two regressors. One is the constant term and one is the error correction term. And these two are multicollinear because the error correction term doesn't vary too much, so it's like a constant. So when you put in both the constant and the error correction, then the constant is significant and the error correction is not. But in reality, which is established if you take more data, the error correction term is significant and the constant is not. So this is something which happens all the time. So just a mechanical procedure where you just allow the data to tell you which is significant doesn't work very well. So you have to have it be guided by theory. If you know that a variable is significant, you include it regardless of what the t-statistic says. Otherwise, you get into trouble. And sometimes, even if the data is telling you that this variable is significant, if your theory says that it's not, you can exclude that variable. That's more dangerous to do, but there are situations when it is possible to do that. So, how does the general to simple method work when, as I've said, there's multicollinearity problem and there's this, that, and the other problem which does arise actually. So basically, it works by the following methodology, which is that you start with the ideal case where all the regressors are orthogonal to each other. There is no multicollinearity. So if all of the regressors are independent, then there's a very nice theorem that inclusion and exclusion of a regressor does not matter. If you exclude a very significant, important regressor, but it is orthogonal to the ones that you are testing, has zero correlation, then whether you include it or not, it makes no difference to your results. So if we start by taking orthogonal regressors, then you can treat each regressor separately. So if I take 60 regressors and they're all orthogonal, then I can drop all of the insignificant ones and keep all the significant ones, and it doesn't suffer from the standard sequential model search problem which arises when you do things by stepwise regression. Because if you start searching, then this has it creates a lot of statistical problems. So the ideal case is when all the regressors are orthogonal, then every regressor gets a t-statistic, and the gets procedure just says that select a critical value and drop everything which has a low t value below the critical and keep everything which has a t value above the critical value. And that gets you your final model in one step. That is very, very important about the ideal case. Now what happens when you have when you have correlated regressors? Then the gets procedure gets complicated, because now you identify a collection of regressors which are insignificant, but these regressors could be insignificant due to the fact that an important variable, that irrelevant variable has been included. So now the gets procedure does what is called a tree search. It says that, okay, this is one possible model and this is another possible model, so I use both of them. And I simplify the model in one way, and then I take into account the possibility that this variable may have become insignificant because of the presence of the other multicollinear variable. So I consider the variables in pairs, and even so, let's think of it with just two variables. It becomes easier. So I have two variables, W1 and W2, and my regression says that W2 is significant and W1 is not, but W1 and W2 are correlated. So I say, okay, let's take the suggestion of the statistical suggestion. I will exclude W1, but I also exclude W2 because of the multicollinearity. So I have now two possible models. So I take these two and then I keep simplifying, and so this becomes a huge tree. It contains, eventually I keep dropping and simplifying, but ultimately I come up with terminal variable models in which I say, okay, I've excluded all the significant variables, all the insignificant ones, and I've included all the significant ones. And now I have hundreds of such models which come at the bottom of the tree after doing selection multiple times. Now I take all of these variables, all of these different models, and I test them against each other following the standard encompassing methodology, and I find out which one is the best, and that is what gets produces. This is called the automatic model selection strategy. Now, as I said, it's not very good. If you guide it with theory, it becomes much better, and it's possible to do that. So, for example, pure statistics doesn't get you to the right result. For example, I just to illustrate this, I ran park consumption on Park GNP and on Honduras GNP. And now, unlike, as I said, you see, Honduras GNP by itself will come out significant because you have omitted the significant. But so the way to fix that is to put in the thing. So I did put in the Pakistan, it still remains significant. Now we have a problem because it seems that after including the correct regressor, it's still significant. So it just means that there are still some more important variables missing in this, and if I include them, it will become insignificant. But the point that I'm trying to make is that if I go purely by statistics, then I will say, it means that the Honduras GNP does have an effect on Pakistan GNP. So pure statistics is never sufficient to lead us to the right regression model. So basically, Honduras GNP is acting as a proxy for some other variable. We don't know. But how do I know this? I know this because of my knowledge of the real world. It's not due to any statistical information. And that is very important, that is not taught in the regression textbooks, that the selection of model is an interplay between knowledge of the real world and the data. It is not purely a statistical exercise. Unfortunately, this is a lesson which is not taught in regression analysis. So the PC Gets does automatic model selection, and it reaches the correct model with high probability when there is sufficient data to enable you to discriminate. If there is a lot of data and there is lots of variation in the data, then it will pick it out. See, basically the crucial thing, which the discussion now is about how much can we trust this automatic model selection procedure when we don't put in knowledge of the real world. So the answer is that if the variables that you're looking at have a lot of variation, then you will be able to tell. You see, if you have variable which is varying a lot, goes up and down and up and down, then your strategy will be able to tell, are these variations causing the variation in the dependent variable? If the variable itself does not have much fluctuation, it is not changing very much, then you can't tell. Basically it's called the explained variation and unexplained variation. So if the variable, if the exogenous variable that you're looking at doesn't itself fluctuate a lot, then you cannot tell whether or not it is an important determinant. And in that case, the get strategy will fail to detect it. Also, the more multicollinearity there is, the greater the chance that the gets procedure will pick the wrong regressor. So if you have two variables which are correlated, the gets procedure could say that this one, W1 is the right one and W2 is the wrong one, when in fact the reverse is true. So the way to do this is to do human-guided model selection. And when you do human-guided model selection, first thing is to use theory to isolate the correct variables. The second thing, which is not so obvious, is to try to orthogonalize variables. So for example, suppose I am running consumption on GNP this year and lagged value of GNP last year. Now this is a very bad regression because GNP in the current period and GNP in the last period are going to be highly correlated. And so my regression will be very imprecise because of this multicollinearity. But I can change this, I can fix this easily. I can say my regressors are GNP current year and the change in GNP from current year to last year. So these two variables capture exactly the same information, but they are going to be now much more orthogonal to each other. So I'll get a much more precise estimations. So this kind of strategy, which is also used in principal components and some other methodologies, but it is useful to do it. Principal components is sort of like magic. I mean, it creates random combinations and it's very hard to interpret. So then that conflicts with the other requirement that you should have some theory guiding your selection. So that's why principal components is not the preferred method. The preferred method is to think about determinants and to try to orthogonalize them and to try to keep them interpretable. Uh, Now, this methodology seems to require a lot of data. So, for example, in the World Bank data set, we have about 60 years worth of data, and we have 62 variables, so you cannot run a regression. So it seems like the GETS methodology would not work, but actually there is a clever idea which Hendry has implemented, which allows you to run his model even when there is more variables than you have data. So this is called the impulse saturation methodology, which I will not go into. I just explained that it is a problem that has been solved. As I said, this a lot of issues related to the general to simple methodology have been worked out. So some final remarks. So as I said, this is currently the state of the art in terms of choosing variables. There are many complications that I have omitted in order to focus on just one idea, how to get the right regressors. But still, there are some very important things that I need to cover to wrap this up. So actually there are two steps to building a good regression model. One is the selection of regressors which I have discussed, and in this we have to avoid accidental correlations and nonsense regressions. So the methodology that I have discussed will give us a model in which the correlations that we see are genuine. See, they exist in the real world. The conventional methodology does not even allow that. It takes what is called spurious correlations. Correlations which don't really exist in the real world but are only a property of the data. For example, there used to be something which was called the Harvard barometer, which the Harvard guys were used to forecast the economy. It was just an accidental set of correlations, and once it flopped very badly and then they stopped it. Similarly, there is this famous accidental correlation that apparently the US president wins the election. Whoever wins the New Hampshire primary for the past 50 years or so has also won the US presidential election. So a superstition has emerged that winning the New Hampshire primary is very important because it's a predictor of the... so this is just obviously spurious, a coincidental correlation. There is no causal link between... because New Hampshire is a very small state, it cannot be a determinant. So this is a spurious correlation. Now the methods we have discussed will get rid of the spurious correlation for the most part. So in the end, when we get a correlation between GNP and, for example, the percentage of confusion, which is turns out to be significant in all of the methodologies. So we will say that the percentage of confusions in the population is a key determinant of growth. This is what we end up by saying. So now we have to understand the difference between correlation and causation. So our methodology can pick up correlations, but it cannot tell us the causal structure. This is very important to understand because especially textbooks mislead and misguide about this. Regressions cannot be used ever to find out about causation because regression only deals with correlation. So why is percentage confusion important? Because China has had a spectacular growth rate over the past few decades, and so this is just the model is telling you that growth rate is correlated with this because China is a star in the growth. So it doesn't mean that if we start converting people to Confucians in our population, our growth rate will increase because there is no causal relationship implied. So I end that here. Now the causal, just a few final remarks that the causality, there has been lots of very new and exciting developments in detecting causality. Unfortunately, econometricians were the first to enter into this field, and then they got badly burnt. The methods that they used, like Granger causality, etc., turned out to be completely useless. So now, but econometrists are suffering from a double delusion. They say we know all about causality, so they are not learning the new techniques which are coming up. So now these techniques, which are based on mediation and moderation to start with, are now widespread all over the social sciences, but econometricians know nothing about them. So we are actually falling behind in this, and this is really the important area for the future, to detect and find out about causal relationships. So I will end this talk over here, and I can invite questions.